Good afternoon, everyone, and welcome to today's SolSmart training on best practices for solar permitting and inspection. Thank you for attending today. My name is Pam Roach, and I work with the South Central Regional Council of Governments on Regional Services. Last week, SCROG hosted SolSmart's training on best practices for solar planning and zoning, and SCROG municipalities that attended both of these trainings may be awarded up to 2/3 of the credits they need for SolSmart's bronze designation. As you can see here on this slide, SolSmart makes it simple to achieve designation by providing free consultation, free technical assistance, and free trainings, as they are here today, as they did last week for the planning and zoning training. SolSmart will provide you with a template for your commitment letter to become SolSmart designated. They will conduct zoning review for you and even forward you a template memo for today's training that you can simply fill in the blanks and email it back to receive credit. Makes it very easy to become designated in your town. SCROG's goal is to have all SCROG towns designated so that, and we're here to support you. Camden and Brantford already received SolSmart designation, which qualified them also for 20 sustainable CT points. Camden actually achieved silver level, and Brantford currently has bronze and will soon have silver. I am also proud to announce that SCROG will soon achieve regional SolSmart designation, and this signifies government progress toward creating a solar-friendly community. To learn how to seamlessly move forward to become designated for SolSmart community, you can contact Toya Baraja at SolSmart directly. Her contact information is at the bottom of the slide. And you may also contact me anytime for assistance. I can help you out as well. So following this meeting, you will receive a recording and the PDF of today's presentation, the link to apply for designation, and the template memo for you to fill out so you can get credit for today. Simple, 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 just fill in the blanks. I would like now to introduce SolSmart speaker for today, Richard Lawrence. Richard is a program director at Solar Institute. He leads the National Solar Jobs Accelerator, along with supporting the Solar Automated Permitting Processing Project, Solar App, and SolSmart program. Richard co-chairs the Solar Energy Industries Association's Quality Assurance Working Group as well. Thank you, Richard. It's all yours. Thank you.
All right. Thanks, Pam. I look forward to talking with you all today and helping everybody meet the SolSmart requirements. I'm going to load up my presentation here. Does everybody see that now? Pam or Danny, can you confirm that? You see the presentation up?
Yes, I can see it.
Yep. Great. All right. So we're going to go over some best practices for solar permitting and inspections. I know a lot of people here probably already have some familiarity with solar photovoltaic systems in particular, and we'll do a quick overview of some of these best practices. We'll go through the guidebook that SolSmart has on this and look at that in a little more detail. This is a relatively quick session. I know we've got 2 hours lined up here, but there's a lot of material to go through. So some of it we may go through fairly quickly, but we are of course available after that at any time to help with any follow-up questions. My name is Richard Lawrence, was introduced here. I've been working in the industry, solar industry, for almost 20 years now, actually. It's kind of surprising. I think I'm at 19 years this month. And my background was in education and training. I have a lot in workforce development. I've taught courses on solar energy installations. I also worked as the executive director of the North American Board of Certified Energy Practitioners, which is the certification body for the industry. So got a lot of technical knowledge there as well. Worked at also at the IBTS, Institute for Building Technology and Safety. We provided a lot of quality assurance services, inspection services for various entities like the Massachusetts Clean Energy Center, NYSERDA, a lot of private companies doing finance of systems. Talk a little bit about that later as well. What I am not is I'm not a code official. I'm not an installer. I'm not an engineer. So, well, I'm pretty familiar with you know, a lot of the technical details here. Some of the questions may get a bit beyond me. With my experience, I'm not installing these things on a day-to-day basis. I'm not looking at them as a code reviewer. So, but we do have a lot of other staff that participate in the SolSmart program. Particularly want to recognize Bill Brooks. He often does these trainings for us. A lot of the material, most of the material in this presentation was developed by Bill, the principal at Brooks Engineering. Bill has been in the industry, I think, over 40 years or somewhere around there, and is an engineer. And you know, with a number of others, particularly on the structural side, created the guidelines that we're gonna take a walk through. Bill does work with us as an advisor and is available for additional, you know, more in-depth technical assistance if needed. If there's follow-up questions that we need to do after that. So we'll do a quick overview. Spend a couple minutes on just going over the SolSmart program to orient everybody to that. A bit of, you know, why are we doing this? Why do we care about streamlining the permitting and inspection process, and why you should care about it too. Then you know, we'll spend a fair amount of time going through the guidelines. They are all online, but we'll walk you through that and, you know, get you oriented to that so that you can then start applying those guidelines and adopting them locally to your conditions. It's broken out into general, you know, requirements for the site, the system, the location, and the building, and then more specific structural and electrical requirements of the systems. And give you a quick intro to Solar App. Pam mentioned another project that I've been working on here for a couple of years now, where we have developed an automated process which just takes all of this guidebook and puts it into a computer program for you, essentially. And we'll introduce you real quick to that, give you some links on where you can find some more information and sign up for that. And then we'll run through the inspection process. I know some staff are certainly more on the permitting side of things, doing plan reviews, and then some are, you know, more field staff. I believe that's generally the case, although certainly some small towns you see some of the code officials doing both of those jobs. Again, a fair amount of content to go through. We've got a lot of slides. We'll try to go through them quickly. We will send you a copy of the presentation. This is also being recorded so that you can go back and reference it there as well. And like I said, we're also available at any time for any follow-up questions that you have. We do have to put up this acknowledgement and disclaimer. So the SolSmart program is funded by the Department of Energy, U.S. Department of Energy. And with that, though, I do not represent the government, and this, you know, nothing here. This is not the opinions or views of the United States government. So. So why are we here? First, SolSmart. So SolSmart is a national designation program for local communities to help them become essentially what we say open for solar business, to encourage and support and promote solar energy in their communities. We have developed a designation program where you earn points for taking different actions that helps to meet these goals here. All of this, as we said, is provided, the funding is through the U.S. Department of Energy, and is, you know, all of these services are free through that funding. So we have a lot of technical assistance available through this program to help you with the different criteria that can help your community, you know, get more supportive of solar. There are currently, we're not quite at 400 yet. SolSmart's been going for a little bit over, I believe, 5 years now. Are we in the 6th year? And have recognized communities all across the country. There's just a couple of states left where we still do not have any designees, but we're pretty close to getting at least one designee in every state. And we do also have one in Alaska up there. Don't have that on the map here. And Puerto Rico is also one of our newest designations down there at the bottom. So, this really does apply all across the country. We've got lots of designees in the Northeast region. And some of the hot spots you see are where we do have those regional coordinators like Pam helping to help, a lot of different communities all at once. So this is great to have everybody sort of working together as a cohort towards these issues and sharing best practices. In general, these actions that SolSmart has are designed to increase transparency, increase understanding of solar, and to reduce any barriers to that adoption. Permitting and inspection do fit into each of these areas, but there are also some other criteria outside of the permitting inspection areas that deal with engagement with the community, engagement with the utility, and other things like that. So we're focused on the permitting inspection with this session today, but there are several other categories in there. Other departments potentially in the community might get involved with some of those other actions. We have a new program guide that just came out last month for the designation. So the criteria has been refined and updated just now, and the new program guide makes it really clear on what these actions are. It also integrates a lot of the technical assistance into the guide now, pointing directly including some of the templates and other resources that we have through that to help with each of those criteria. So there's 75 different credit areas in these 5 main categories. The foundational categories, permitting inspection is one of those, and so there are requirements within that category for meeting any of the designation levels. You get points for completing those categories, and like I said, completing this training today is one way to get some points, because training your staff is one of the important things that is incorporated into this designation program. There are also other areas, like we said, on market development, community engagement, and operations of the government itself that might be different departments there that deal with that. Also, of course, planning and zoning is really important for solar's deployment, and making sure that the zoning rules are favorable or accommodate solar, allow it by as right in most situations and things like that. So program guide, again, the best resource for understanding what all the different points are. So if you're new to the program, make sure to get in there, check out the program guide, and look at all of the options and how you can get involved there. All of that's oriented towards getting a designation. As you saw, there were different colors on the map. We have bronze, silver, and gold levels. Each level does have some required sections. So you have to complete, like I said, in that in those core criteria of like permitting inspection. To get bronze, you need 20 points in that area. And then there's some additional building on that to get silver and gold. With gold, some of the criteria, for instance, does require that you do implement some procedures that result in a turnaround on permitting of no more than 3 days, for instance. So as you go up in these criteria, some of the things that you need to meet become obviously more, more favorable towards solar deployment. The program is actually 2 awards from the Department of Energy. One of those is the Technical Assistance Program, and that is what the Solar Foundation actually leads. And with, again, a good group of technical advisors, well respected in the industry across the country, including the National Renewable Energy Lab, as we said, Brooks Engineering before. We've got several of the community groups like NACO and NLC, and industry experts at CADMIS, RIP, and SEIA, the Solar Energy Industries Association, and also EPRI. So, good team there. We've got a lot of smart people beyond me that can help with all these different aspects, from, again, permitting, inspection, planning, zoning, community engagement, all of those areas. They've created a lot of resources that are available. And, we continue to do the work and help communities with getting any aspects needed to, take those actions. The designation program administrator is ICMA, International City County Managers Association, Management Association. They run the actual designation. So they're the ones that review the applications and then actually make the determination that all the points have been met, and give the award and maintain that database there. So that's their primary role. We do also work with them, the Solar Foundation, as one of the subrecipients on that side of the project, to help with the designation process too. As we said, our Solar Foundation is mostly focused on the technical assistance side of things. Saw the logos of some of those people we have in our team. They can help with various aspects, things like site plans, doing a site assessment for renewable energy projects, looking at the feasibility designs, policies, obviously the planning and zoning regulations, all of those items, these permitting and inspection best practices that we've developed through this and are implementing. Lots of trainings available and webinars on our website, a number of white papers and other resources there. And again, continue to be available to people working towards the designation, as well as once you get designated, we continue to provide some services as needed there to continue as you implement these things to look into if there's any questions you have and other actions you want to take. Again, work with our technical assistance team, can work with anyone in the staff at your community, and all of this is provided at no cost, funded by the Department of Energy. So the main thing, on your side, the communities have to do is provide that staff time to implement those policies. So to work on, some of the tasks that we're going to talk through today and others. But the technical assistance and all of that is provided at no charge. So lots of good resources online. Feel free to reach out to us at any point if, again, you have additional follow-up after this intro session today. Let's see, I think it might do it when you get the webinar or this presentation here, you'll get these links, but solsmart.org is pretty easy to remember, and that's where you'll find all of this. And in particular today, what we'll be talking about is the guidelines, and you'll find those there as well. But also, several other webinars that have been recorded on a variety of topics, including both permitting inspection as well. So more in-depth resources, please check out the website for all of that. So why are we here? What are we talking about? So first, quick overview. I think most people are probably familiar with this at this point, but there are different types of systems that are out there, and they do continue to evolve over time as equipment develops and new codes are put into place, et cetera. So we're talking about photovoltaic. That's where the PV comes from. And PV, it does require some specialty knowledge to certainly to review plans and to inspect the systems and ensure they do comply with the code. Primarily, starting off with photovoltaic panels produce high voltage direct current electricity, although some of them do certainly have power adapters, inverters on each module and actually produce AC power. Most systems that cells themselves produce DC power, and when combined together can produce very high voltages and lots of energy. DC currents are something that aren't as familiar typically to most electricians, and the rules around DC circuits are often less familiar for those in the planning and in the inspection world. Often have come from the construction industry, maybe very familiar with AC circuits and standard residential and commercial wiring practices. While all of those certainly do still apply in photovoltaic systems, there is an AC side of things that has to be connected. There's often a lot of DC circuits as well, and that does require some different understanding. They are powered by the sun, and there's some interesting aspects there that make them different from other power sources that are run through generators and stuff producing AC power. They're variable in their output. The more sunlight you get, you can actually get increased output beyond their basic ratings. At colder temperatures, they're going to operate at higher voltages. At bright sunlight conditions, they can operate at higher than rated outputs. So they're widely customizable, lots of different configurations. And so there tends to be a few standard things. We try to put it into a standardized box for the simplified review, a few different configurations in order to do a simplified review process, but they can get pretty complex, especially when you start adding many systems today are starting to incorporate energy storage technologies and other things like that, where some of the codes and standards are still, evolving and being developed more. So there's definitely different grounding considerations, safety issues that need to be aware of. They do produce power. You can't just shut them off. If there's sunlight shining on them, there is electricity energized in the system. So the technology does evolve fairly rapidly as well. The code changes, every 3 years. There are some differences that need to be, taken aware of. Not as much in this last round, but again, like energy storage is another area where we're seeing pretty rapid development, both in the technology and the codes and standards around that. So there are areas that you really do need to, stay on top of with education training. That's why we have that criteria to make sure that this is, an important factor. And quick illustration there, everybody's aware of the experiment. You take a little magnifying glass and you collect the sunlight that goes through that little round circle, and you can focus that energy, onto a small dot. Well, imagine that magnifying glass being the size of your entire roof, and the amount of energy that is then concentrated into one little wire going into your house. And so, these are powerful systems, and they can, it's important to make sure that they're designed and installed properly to avoid, as we call them, thermal events, which are certainly possible with this equipment. But when designed and installed properly, obviously following the codes and standards that are in place, they are very safe and reliable systems that can produce this significant amount of energy over literally decades of time. So why simplify permitting and inspections? Well, you approach this from the the industry side of things. It's all about reducing costs, right? Reduce costs, reduce costs, reduce costs. Well, there's layers to that. There's different ways in which costs are reduced. One is just by having a more standardized process. There's literally thousands of jurisdictions all across the country. If each one implements their own process, which they often do, it's just challenging from the industry to understand what those processes are, understand what needs to be submitted. One jurisdiction needs this, the other one doesn't care about that, but wants this. You know, the different forms, different processes. The more things can be standardized there, certainly the easier it makes it on the industry. Having consistent application requirements, things that you're going to be looking at and concerned about, while the code is the same in many different places, it's interpreted somewhat differently. There's a different attention placed on things. You know, again, creating more standardized process reduces that complexity in terms of just understanding what's required, right? Starting off with that transparency piece that we were looking at. You know, having a more standardized, streamlined process is going to then, of course, reduce staff time involved in preparing those applications, in submitting those applications, and getting in inspections completed, getting those permits completed, being able to schedule the jobs reliably, and all of that results in a greater customer satisfaction. If you can turn around the system more quickly, your customer is going to be happy rather than waiting a month down the road to see, well, we're not sure when we're going to be able to do the job because still haven't heard anything from the town. So getting that quicker turnaround does result ultimately in increased volume of jobs that can be installed by your crews, and happier customers results in more referrals. Shorter duration times result in less cancellations during that delay that may be experienced, and so you have again more jobs to do. So again, all this, we know that many in the permitting inspection world, the code department does not really care if the company makes money or not. But from the SolSmart perspective, where we see communities who do want to increase solar energy for a variety of reasons, these types of actions are ways that can make a big difference in communities. The soft costs associated with solar is all of the the non-hardware hardware costs. So that includes customer acquisition, but also, of course, all the time and effort in permitting, engineering, design, et cetera, that are all tied into this permitting inspection part. Those soft costs account for actually the majority of the cost that the consumer pays. And so average of 67% at this point is your staff time. That does include labor, I guess it's installation labor. But the hard costs have, equipment costs have continued to decline fairly rapidly. That soft cost portion continues to operate at a higher percentage of the total system costs that the customer ends up paying. So switching, again, building perspective, there's lots of reasons to implement a streamlined process as well. Having this process reduces your training needs. It also results in you getting better systems to review. Having that standardized process, again, the installers that are working across multiple districts, jurisdictions, it's really hard for them to know what one jurisdiction wants from the other. And so having that consistent process, that results in, you getting potentially, applications that aren't exactly what you're looking for. But if everybody can kind of harmonize around a standard process that's going to work, that makes it a lot easier to make sure that you get the information that you need as well. It allows you to focus your effort on, we're looking at here more standardized, regular, we call them cookie cutter type systems, right? But there are certainly more complex ones. You've got lots of other projects to look at as well, of course, that aren't solar. And so, streamlining and improving the speed and efficiency of processing these applications can allow you to focus your staff time on other areas. The other big piece is being able to handle increased volumes. We'll see next slide on here. Next is, the solar installation continues to increase, and we see, there's plenty of examples out there of jurisdictions where literally half and more of the work that their department does is, or at least the number of permits that they process, are solar energy installations. As this becomes more and more common, as the costs continue to drop, we start to see rises in, these things. And also you see increased installations when you do improve these processes. We've certainly seen examples, or actually the majority of installers that we've polled say they specifically avoid jurisdictions that have challenging, complicated, onerous processes, the long delays, high costs of permitting, all these things we're trying to avoid through here. The industry tends to try to stay away from those towns and not really focus their sales efforts there. So if you can have a better process, you'll have more business coming. You'll have, with that comes that economic development and progress towards clean energy goals. That may not be the the goal of the building department, but it is often the goal of more of the executives, the councils, the mayors, et cetera. And so the building department supporting those efforts makes you look good in their in their eyes. And can result in obviously more greater health and safety. Having a reliable system to review and permit and inspect these standardized system, you're going to catch the common mistakes, and you're not going to get systems through that are going to be unsafe. Again, quick, so prices, this first chart here, prices have declined, they continue to decline, and with that, the installation rates have gone up. Top chart there showing sort of in the past, and the bottom chart there showing what's projected in the future. The current administration has a goal of getting us up to 8 million installations within the next 5 years. To put that in perspective, through the entire course of the industry, we reached 2 million installations last year, or well, in 2019 actually. So we've, in all of the, couple decades, really the last decade of time, we've installed 2 million installations. The intent is to be at 8 million in the next 5 years. So there's some other policy aspects even after this chart's been created, where some of the investment tax credits, the ITC, has been extended for a couple of years. Those are all putting upward pressure on these charts. We're going to see lots of growth in the next couple of years with this price coming down, with the tax credits still available, with favorable policies, in the clean energy agenda of this administration. The volume is increasing, and the better prepared you can be for that, the better position you'll be in. And just quick look at the price here. While certainly not all of the effects are on permitting and inspection, those soft costs really drive up the cost here in the United States versus really the whole rest of the world. I mean, some of this there are some tariffs on equipment and things like that make our costs, our hardware costs, a little bit higher than other areas. But permitting and inspection, some estimates put it at, somewhere between 50 cents to $1 per watt, which is, several $1,000s per installation that can be wrapped up into that. And so, it is possible to get the cost of our systems down even substantially more than they are already. And that, again, in turn drives the installation volume that you will then have to handle through your permitting processes. So the more streamlined you can be there, the better you'll be equipped to do so. Finally, here as well, there's lots of room for improvement on the code inspection. Implementing these standardized processes helps to improve that health and safety outcomes. And, over the years, a couple of groups in particular, Cadmus Group, who again is one of our advisors on the project, IBTS, who I used to work with, they've inspected thousands and thousands of systems, tens of thousands of systems across the country, all different states. Same thing is shown there. This gets to that, again, complexity of systems. All of these systems that they've inspected have already been gone through the permitting process, been approved, and inspected, signed off, and it took, approval to operate. And the majority of those systems have some deficiencies. Some of those are minor. Debate whether having the right label on a system is minor or not, but that's generally considered a minor thing. That's where labeling is the biggest area where you see deficiencies. But there are a high percentage of systems out there that have been approved and inspected that do have significant issues. And we'll look at a few of those key areas here. Wire management in particular, also roof penetrations. Problem with both of those is they tend to be on the roof. So finding ways to check those is important to do. Some of the other areas of grounding and interconnection, those are easier to look at from an inspection perspective, but lots of room for improvement there. Now, thankfully, we have had relatively few thermal events like this one pictured, but again, that is a lot of energy going through these systems. And when you have loose connectors, when you have dangling wires rubbing against sharp objects like the edge of modules and such, abrading against the roof surface, you have things where they're not installed properly. You can have leaks, you can have physical damage, and of course you can have fires created. So it's important to look at this stuff well. Quick overview of some of the things here. Some of the best practices, a summary is to first off, put your, make sure your requirements are clear and that they are available online. This helps with that transparency piece again, making sure everybody knows what to expect. That's the biggest thing that installers want to know is, what do you want? And if you can be clear about that, if you can post it online, and it's not a guessing game in terms of what you want in your applications, what you want in terms of your system designs, that's actually the biggest factor for installers, is to really have a clear sense of what's expected of them. Implementing this expedited process we're going to talk about here can improve things a lot. Utilizing that standard permit application. Connecticut does have a standard permit application form. We recommend everybody adopt that one. There are certainly some other examples out there. We've got some templates too, but it's good we do always recommend to use the one that's used regionally. So New York, where I'm based, we've got the unified solar permit here. Connecticut, you also have a standardized permit that was developed by the state a number of years ago to collect the information. The more the communities can get in line with each other, again, the better that is for the understanding what's needed. We encourage everybody to do things through online, and lots of communities have been moving in that direction, certainly in this last year. And that also results typically in faster turnaround times. It reduces truck rolls, having somebody drive to the office to deliver the paperwork, and other aspects like that. Even if it's just an email process, that is preferred, certainly, to having to turn it in paper in hand. From that, though, make sure that when you get that application, you are able to review it quickly and turn it around. Best practice would be, best practice is automated, which we'll talk about later, where it's turned around literally instantly because all the plan checks done. But others certainly can do over-the-counter reviews in 15 or 20 minutes and go through the checklist for standard systems and get them reviewed pretty quickly. Turnaround times of a day or two are certainly in the best practices, but even if you're using an online system, you get that application and then it sits in the queues for 25 days. That's not serving the goals here. So along with that, charging reasonable fees, making sure that those fees are in line with the work involved. And by streamlining this process, you can reduce your staff time. Many people can then reduce the costs of those permits, but even if they don't, you keep that same permit fee. You do that job in 15, 20 minutes instead of an hour or two. And, you're doing much better there economically with those fees. So we want to keep them low. There's certainly examples in Connecticut and other places where communities have exempt fees. There's no fee for these residential permits. In that case, obviously, you want to be as efficient as possible as well. We want to limit any local requirements. Obviously, there are local zoning aspects, and you get into historic districts, things like that. But generally, we recommend just implementing the model codes as written, so we have a standard set of requirements everywhere. Some jurisdictions start to put in special requirements that makes it more challenging to keep track of and to enforce, understand what the rules are. We want to limit or just not have any local requirements and utilize those statewide and sort of national requirements. Recommend only one inspection, not doing inspections, rough inspections, and not having separate inspections for structural, electrical, fire, etc. They often have to deal with even another inspection from the utility already, and so limiting the number of inspections. We'd also say limiting, I have it on here, having only one application process too. If you do have different departments, like fire department has to review and the building department has to review, make sure that we can do that through one application and review process. Getting the inspection, recommended to do narrow window and turn around on that request. Ideally, being able to do that inspection next day or even same day. Some inspections are able to be scheduled same day, and particularly as you start implementing some remote options for inspections. They're a lot easier on your staff to schedule and do as well. And then, as we have doing right now, the last one there, provide training for staff on solar, as we've talked about. So that's a quick overview. And actually, we'll go a little bit more here. We're going to go into these guidelines more. You'll find them, again, solsmart.org/permitting. This is where, again, all of this information is. We are going to have to go fairly quickly through the checklists. And so there is, just give you a quick orientation to what's there. The guidelines, SolSmart guidelines are broken out into, the first is just basic information you need to collect about the system. Then the two main components, structural review checklist and electrical review checklist. Those are the main areas we'll look at here. And with each of those, there is the basic checklist that sort of outlines, in bullet form. These are the requirements. Those are sort of 1 to 2 or 3 pages each there. Really, it's about 1 page on each section, depending on what type of system you have. And but they're for your research, for your understanding and comfortability with these processes, we have these commentary documents that really go in depth into, okay, why is this requirement here? Why are we saying we have to do whatever it is? We'll look at those. Each of those requirements there has anywhere from a paragraph to a page or more describing, how we came to that, that level of detail, what's needed. And that will explain a little bit more of that there, but that's the overview of what we got here. 3 steps. First, collect information. Second, do a structural review. Third, do electrical review. These guidelines, again, ways that you can confirm code compliant systems. They apply to most residential. They could apply to some small commercial systems. And in general, they're intended to be applicable, again, to the majority of systems. We're talking, somewhere at least 75%, if not certainly more in some of at least residential systems for sure. that are going to meet these criteria. There certainly could be systems that don't meet these criteria, and those can be code compliant as well. They're just not going to be able to fit through this streamlined system. And so, with that is recognition that the guidelines do provide this sort of box in which systems can qualify for this streamlined review process on your end, and sort of streamlined application process on the customer, the contractor's end. Based on that, though, this is not designed to then limit systems only to those that fall in those categories, because that would then create implicitly some additional requirements that don't actually exist. We do have to limit some requirements in order to have a streamlined process. And so, but that doesn't mean that other systems that don't fit into here, wouldn't qualify. So we don't, we want to make sure that that's not confined and restricted to just these types of systems. There's certainly others. We'll look at a couple examples here. But the guidelines, again, the intent is to make sure that the code requirements are followed. And this is, obviously the National Electrical Code. Article 690 is the one that primarily deals with photovoltaic systems, but also, of course, other aspects of the code are relevant in terms of, wiring, conduits, etc. So the other chapters there as well. The International Residential Code, International Building Code, and International Fire Codes. Those I codes are, what are more on the structural side of things, and also the the fire pathways. So more recently, last few years, last 5-6 years, the fire setbacks. There's been some changes there, some things to look at, and again, these are intended to look at that. We have a fire bulletin in the guidelines that outlines those as well. And ASCE 7 deals with wind loading of systems. So that's more that standard. That standard's referenced by these different codes. And so, with this, we recognize, so I think this might be some duplicated material here, but, oh, actually, no, the point here is, we are looking to actually eliminate some of the engineering requirements. So if you can show that, if something meets these streamlined guidelines, that should eliminate the need from the inspector's point of view to have an engineered stamp of those plans. Again, this commentary we go through, all of these explanations show very clearly how if a system meets these guidelines, they will be code compliant. They will be designed for this system. Now, if systems don't meet the requirements, that is an area where you would need potentially some additional engineering review. Now, that's not to say that this is not, circumventing engineering process. All of these systems, have been engineered at some level. The equipment, the designs they're using to do the layouts, and all of that. There's been engineering that's gone into all of those aspects. So the point is to not require a specific engineering for each specific, house or dwelling structure, each different system that's proposed. That if we can put them in this box, we can trust that the engineering around that. Again, the commentary shows you the calculations, a lot of effort, particularly on the structural side of things with this last round that, again, is intended to make you trust those, and that if it fits in that box, you can be assured that it is going to meet those requirements and it is within, safely within those parameters that are needed. So other aspects, like we said, using that eligibility checklist, there are certain projects that are going to qualify, others that aren't. So we've got those checklists for you. With the system, with this design, the guidelines, there are also standard plans to be used. And I know the Connecticut guidebooks have a lot of this same stuff. And so a lot of those standard plans are helpful in terms of getting the information that you need in a consistent manner, and also giving that consistency to the preparation of those documents for everybody. Again, putting those stuff online is recommended, being able to submit it electronically, doing this process. Talked about a number of those other things there already. Fees, I think this is just going a little more in depth. And training, just a little more detail on what we've covered, so I'll skip over that. Here's the box of the standard requirements. So first off, system size of 15.36 kilowatts. Where that number comes from, that's essentially the maximum size you can put onto a 400 amp service. If there's a smaller service there, the system will inherently need to be smaller, but that's the maximum size that you could expect to be able to fit under, again, these guidelines here. There may be some other ways to do that, larger than that. There's certainly ways to do larger systems than that, even in a residential setting, and be code compliant, but that will require additional, sort of engineering review. We are also specifically looking at 1 and 2 family dwellings, so this doesn't really deal with commercial buildings, unless, again, it's sort of similar construction. So wood framed buildings, similar size, so dentist office, things like that, might, while they're commercial in terms of zoning, the structure is essentially a residential building, a similar type of construction. So that's what we're looking at. We're not doing flat roofs, that type of stuff. Also not doing ground mounts systems with these. So these are rooftop on a, essentially you can have different types of roof materials, but the framing does need to be, wood construction there. There are a couple of different designs electrically, string inverters, systems with DC converters, and then microinverter based systems. What you see excluded here is things like hybrid systems that might have a generator, systems that have batteries, other things like that. So with snow load is the guides can be applied to up to 60 pounds per square feet. So pretty sure that covers all of Connecticut, and that really you don't hit that extreme snow until you're getting farther north and into the mountains. Up in Maine, we do see some areas a little bit higher than that. Certainly some areas of higher elevations, but don't believe anywhere in the state of Connecticut you'll see that. Also, wind speeds 150. Now there are some extensions of that where you can go up to 180, and that should also apply to the whole state there. Some areas you may end up with locations. So all of these are wind categories, A, B, and C. There's some slight variations in terms of requirements. If you're in a category like C, but category D is not going to fit in this. So, you may see some systems. Category D is that you're within I believe 200 yards of an open water, essentially. So some coastal properties, you may see that. Those would not be able to fit through this box. And obviously, there's other requirements we'll look at in these checklists, but those are the main box there. So again, this is intended for the vast majority of the country, vast majority of systems that are installed. Certainly, as we get towards points in like southern Florida, we're going to start seeing much higher wind speed loads from the hurricane prone areas there. You get out towards like Nantucket and such, and some of those, again, coastal areas, you may be on the border a little bit, but in general you're still going to be within that 150, but you may be getting into a category D on the coast. Examples, some of these systems, we mentioned a few that don't fit. Energy storage systems, currently we don't have a streamlined process for that. There's certainly efforts under the way to develop those, and hopefully within hopefully the next year or so, you will see that. One of the things I'll talk about, the solar app. So automated process does incorporate storage, or will be launched very soon. So that is an option to do that. Things like the building integrated arrays, as you see there in the picture, that Tesla roof, where it's actually, the roofing structure, that is not fit through this guidelines. Not to say again, these aren't bad products or weird products or anything like that. They just don't fit into this box that's been created. So again, ground mounted arrays, again, excellent, lots of good reasons to do ground mounted arrays. They certainly aren't as common, primarily due to the increased cost of trenching and structural, foundations, et cetera. But, they're just, again, don't fit in this box. Doesn't mean you shouldn't allow them and shouldn't permit them, and that they can't be designed to be code compliant. Awnings, carports, shade structures, things like that. These are all over the boxes designed here to be attached to the roof of a structure. Does not allow main panel upgrades. Some systems, if some of the older housing stock may need to upgrade the panel there, that upgrade of the panel may need to be looked at in terms of some additional codes that this box is not doing. And if you've got an existing system in the home, again, some examples here, you're trying to add a second system. All the calculations here are only based on, having this one system and not understanding what other impacts there might be. We're going to walk through the structural checklist. There's some general site requirements, requirements of the structure itself and the array that are going to sort of apply across the board. And then the structural is divided into what's called member attached provisions, sheathing attached provisions. So you look at the chart, the top picture there, it's typical installation. This is before the panels have been installed. You have penetrations into the roof, attaching the system to the roof. These can be attached either into the structural members underneath, so drilled into those, the beams there, or there are systems that can be installed just attached to the decking, the sheathing itself. And there's benefits and the pros and cons of both types of installations, but the member attached are certainly stronger. You're attaching into a just for by attachment point type of thing. That you're attaching into a stronger structural component, and so with a deep lag screw versus a shorter, shallower screw into a thinner piece of material in the sheathing. But both systems can be designed. You'll see, higher, like we saw, you can go upwards of the 180 miles per hour design loads if you attach to the members, whereas the sheathing attached, there's some, additional considerations for the wind loading on those. The electrical, there's just general electrical requirements, and then separate requirements for systems that are either the string inverters, which is where you have, sort of that one large equipment where all the DC power comes into, and then that's where it converts it into AC power. So it's sort of a centralized unit versus the microinverters or AC modules, where you have a smaller inverter on the back of each panel, or maybe two panels, and those convert the sort of per panel into the AC wiring. AC wiring comes down. There's so different electrical schematics and different electrical requirements associated with each of those. You can do both string and microinverters as either supply side connections or load side connections. So load side is where you're plugging directly into your service panel, your load center, and adding another breaker there. The supply side connections are going to be connected directly to the supply in between the panel and the service entrance. Starting off, goes through the information you need to collect through this process. First is that permit application. That's going to be your basic information, the address, who the contractor is, what type of system it is, and what their license number is, et cetera. Recommend, again, that standardized permit process the state has available to you, or one similar to that. You need to collect site plans. So those are going to show the location of the material, the components. These are important for some things such as the fire setback requirements, but just understanding also where those components are going to be located, and that they, for instance, comply with some of the working distances and things like that you might need to look at. The electrical diagram, we have, again, standard. These are fillable format, standard electrical diagrams. If they comply with one of those 4 system types, they will be able to, fill out one of these diagrams. There's some other things like the number of modules is going to be limited to a couple of strings per inverter. And so, some systems may not comply, even if they are like a string inverter, with these standard designs, but those standard designs certainly help, again, to collect the correct information, all of the information that you need to do the review, do it in that standardized format, and in a way that, you're going to just see the same thing over and over again. So it's going to be a lot easier to review than, random designs that you're going to get if you don't use a standard process like that. It becomes more difficult to find the information that you need. And of course, product specification sheets and manuals. Often the code says, or the requirements say that things need to be installed according to the manufacturer's instructions. And so having a copy of those manufacturer's instructions and the specification sheets to verify the ratings of the equipment, et cetera, is going to be needed. So making sure that you have a method to collect those is going to be needed. So, and I guess we did not mention it before, but if you have any questions, certainly go in the chat function. Or I guess we can take a minute right there. I know we've got a lot more to get through. I'll try to just go through quickly, but if any, is everybody muted, or do we have to unmute? Are they able to unmute? No.
I think, Richard, maybe the best way to do this is just to direct everyone to send their questions in the chat, and then we can read them out if that works for you.
Yeah, sounds good. Certainly, like I said, have plenty of additional material to get through. Again, all this stuff that we're going to walk through real quick right now, you find more detail online. You can get the full commentaries to understand. I direct you there first to any of these things we're about to cover in terms of the requirements. All right, next page. Why is it not progressing? There we go. All right, base structural requirements. First assumption, this is, like we said, residential. It is going to have a single layer of roofing. If it's got, composite shingles, they can't have already installed a second layer. It needs to just be one layer because of the added, weight there. Sheathing needs to be at least 7/16 inch thick, and these modules need to be mounted generally flush to the roof is what it's called, but there's always a sort of a gap under the modules, anywhere from 2 inches to 10 inches off of the roof deck, and then some of the parameters based on how high that is, but that allows some wind flow underneath to cool the panels, and just the way that they're the materials in order to attach to the roof, like we saw. So distributed weight of less than 4 pounds per square feet. This is almost all systems are going to comply with that. Once you distribute that weight out, the modules are not that heavy. Tends to be closer to half of that in most instances, 2.5 pounds. So you rarely get anything upwards of that height. We're essentially assuming this is a structurally sound building to begin with. So it's been permitted it's a code compliant structure to start with. That would include, rafters no more than 48 inches apart or closer, which again is the vast majority of houses that are out there. Certainly, you may run into some older households, but if you've got a building that's structurally sound, often those older households had was it more sturdy wood that was used, older growth wood, larger structures, larger members of cuts of wood that were used. And so, again, vast majority are going to comply with this. They do need to be less than 40 foot high for the member attached with that mean roof height, not the peak, but the mean roof height. Again, most of your residential structures are going to qualify with that. Again, you start to get to some of your big mansions on the coast, maybe not, but this is not what it's designed for. And then we don't really have to deal with seismic activity in Connecticut much, but in some areas where you have higher seismic activity, you don't want to put too much more weight on the roof, so it limits it. This box again limits to no more than half the roof surface covered, so you don't have more of that added weight that can imbalance things under a seismic event. We've got a whole list of these specific details here. Just in interest in time, we're not going to go in real detail onto each of them. I just want to give you sort of an overview of what these guidelines are looking at, so you understand that. Again, each of these points that is outlined here is explained in more detail sufficiently in the commentary, and says, okay, this is why we've asked for this point, and this is how we got to this being the requirement. It is intended as a caveat that with this is based on nationally. So some of these standards are based on what is the highest temperature that you're going to encounter in North America or in the United States. So we're looking at temperatures that are based on Palm Springs, California, right? Desert Valley, Death Valley, essentially. That's we're not going to see those temperatures up here in the Northeast, right? But the standard here is based on that. So there are potentially, some of these things could be pushed in a different direction in certain areas. So you're not going to see that heat up here. So, some of the things around conduit fill or something like that could be slightly different and could be outside of what this box is asking for in the Northeast. But if they comply with this box, then it's safe, because it would be safe in Palm Springs Desert. Same side is also maximum cold temperatures. We've designed it there so that these systems, you do temperature rating through the process. So they do have to design the site-specific cold temperature here for some of these things. But main thing with the structural array, the solar panels act as essentially a sail. There's two things you're trying to do with the structural. One is make sure that the array does not act like that sail and actually rip up. So it's uplift forces of wind coming underneath the array and pulling it up. And so some of the things in terms of the attachment points are based on that. But the other aspect is also when you get into like the snow load and wind loading, that you want to make sure that is more of a downward force, and pushing on that array. In general, obviously the structure itself was designed to withstand the downward pressures of the snow and the wind that is going to be encountered in that area. But when you put a PV array on the structure, you have to now attach it at certain points, and you want to make sure that those points are not going to be overloaded. And so there's some of the guidelines here look at in some aspects you want to make sure that you're distributing all of that load properly. So setback from the roof edges is important in terms of that wind loading and getting wind under the array. At roof edges is where you see a higher pressure developed under strong wind conditions. And so setting back slightly from that edge, and that is going to be, again, based on the height of the array. So the taller, you start to get into that 8, 9, 10 inches off the deck, you need to be a little bit farther back from the edge to avoid that concentrated wind effect at the edges. You get closer to the array, you can get a little closer to that edge. You don't want to cantilever over perimeter anchor. Again, doing wind loading at the end, you don't want the flexing of the panels, more pressure to be created to be able to bend things there and lift edges up. Edges are always where you're going to have more challenge than in the center, particularly with the wind loading. Gaps under the module, again, all this is related to your wind uplift. Once you start getting above 10 inches off of the deck, you have a lot more opportunity for wind to get under there and create a higher uplift force. So keeping it shallower is going to help prevent that. So, and then also these gaps between the modules, why we have specifications on that is looking at, again, airflow. If you have a single sheet, large sheet that is unbroken by these gaps, it is harder for that wind to get out, and you can have greater uplift pressure. If you have cracks in the wind, that pressure that builds up is able to escape through those cracks and not develop into these sort of extreme categories of events that helps distribute and diffuse some of that. So there's some requirements around gaps between the modules and how those can be put there. Always want to make sure that the rails are running perpendicular to the rafters. This is, again, for sort of distributing those loads more evenly. If you've attached that single rail across multiple rafters, any uplift force is going to be distributed then across those rafters. If you're putting them in parallel to those rafters, an uplift force potentially on like one side of the array could result in issues there. Also, downward force is the same as well. And I think that's good there. Again, following manufacturer's instructions, that's going to be a big piece here. And so with the fasteners, if you are doing a member attached, you want to see that that's at least a 5/16 inch screw drilled in at least 2.5 inches deep into the structural member. So that often results in the lag screw that's in the orders of 4 inches deep, because it has to go through the material of the footing itself, has to go through the sheathing, go through the decking, and then that's when you then get into 2.5 inches of depth. So the screw itself will be longer. Or, again, follow manufacturer's instructions for the both the spacing and the type of fastener. The sheathing attached fasteners are again, more just screwed directly into the decking. That's the depth of the penetration there. With the member attached, you can go up to 180 miles per hour. To do so, you have to set that array back from the roof edge. It's called wind zone 1, is anywhere within 3 feet of any edge. And that, again, is where you're going to see the greatest wind pressure. Removing the array from that zone is going to reduce aspects there. The height is reduced of the structure. Again, taller structures are going to be exposed to greater wind. Try flying a kite near the ground, doesn't work so well. You go up higher, you have higher wind speeds. So even that, that 10 feet there can make a difference in that regard when you start talking about these greater wind speeds. And here the cantilever is reduced to only 6 inches. So you can't have the edge of the array start to hang off more. You want to reduce that so you don't get that wind being able to go there and not have an anchor nearby. Anchor standoff spacing as well, you cannot exceed 2 feet. So want to make sure that it's just, you got to have a lot more attachment points to be able to withstand those higher wind speeds. So now you're talking 2 feet apart. There are some options. Don't even really need to talk about these, although, yeah, because you're not going to go into the low wind speed in Connecticut primarily, or well, I guess, or snow. And so, but down in the sort of southern part of the country, southeast, you can run into some areas where you can sort of reduce some of the requirements because they don't have much snow. They don't have a ton of wind either once you get away from the coast, and so there's some rules around that, being able to allow longer spacing. I won't even go into that. You can look at that if you want. So here's the sheathing attached arrays. Again, those now you're attaching directly to the decking, so slightly different requirements there. You still need to set the roof back from the edge at least twice the gap. You still need to not avoid cantilevering. That's the same. Now the gap under the modules is 5 inches. We want to reduce that, the ability, the wind to get under there, the uplift forces that you can get if you get closer to the roof surface. So now we're going down to 5 inches. That gap between the modules also has now increased a little bit. So gaps need to be wider. All of this is in an effort to reduce that uplift wind that you can get under those modules. And also need to be attached on a sloped roof, not a low, go down to low pitch at 212, but that's the lowest. There is some detail on the type of attachment of how the roof framing and the sheathing was attached. So here, you're attaching to the array to the sheathing. What needs to be looked at is making sure that the sheathing is nailed into the rafters with, you need to understand sort of what's holding that sheathing down more to those rafters. With a member attached, that's not important because you're attaching directly to the rafters directly. With a sheathing attached, you do need to understand a little bit more of the structure itself in terms of how is that sheathing attached to the rafters, and making sure that you've got an option that will hold that decking down with the potential added uplift of an array that was not originally planned in the design of the roof. As you get into the sheathing attached structures, you also come up with this thing of the bands of strength. So attaching to the middle of a decking, a sheathing will result in a stronger attachment. You got to the corner and you can bend and flex it and sort of break it a little easier. So there's some rules around where, in terms of those anchor locations are, whether they're in a band of strength or not, and sort of how you can, where you can do that. That tributary area as well starts to become important in terms of around each of those attachment points and the space that you have there. So yeah, some requirements around that. You need to check off each one of these. If you have an array that has the anchor points within those bands of strength, in the middle of those plywood or OSB sheathings, you can meet some requirements. If you start to go away from those bands of strength is the next option here, then you need to be a little bit more concerned about the strength of that, being able to withstand that pull out. And all of this is that connections are able to handle a certain uplift force that you're going to see. All right, so again, two main categories there, the member attached and the sheathing attached. Now we'll look quick at some of the electrical requirements before we go through a quick walkthrough of an inspection. So electrical components, right off the bat, main thing, all of them need to be identified, listed for use in PV systems. You know, you don't often run into issues with this, but sometimes some new components onto the market, things like that, you know, you want to make sure everything's listed. Also, the array mounting system needs to be UL 2703 certified. This is related to the bonding and grounding of that. If the array system itself is not listed, again, most of the major manufacturers are, but if there are some that aren't, that system itself is not, that you can use a device to connect those together that is listed, that does meet the requirements. Here's the thing, electrically, no more than 2 series of modules together, 2 series strings per inverter input, and no more than 4 strings per inverter, so no more than essentially 2 inputs. Now you can have a 4 input 4 input inverter. Those do exist, but you can't put the multiple strings on each of those. You'd have to just one series string going into each of those inputs separately. And each input measures, one, electrically, it allows certain voltage and such, but also often they track power production. They maximize production at each of those string levels. There's different requirements here around the types of wiring that's allowed, and in different sections of the array. So the source circuits, PV source circuits, those are the ones that are coming right out of the module. Those are the DC circuits, and they are often, they are exposed locations, need to be UV resistance, etc. So those have to be PV wire. That's the only thing that is allowed in those areas. Once it goes into a raceway, then you can use the THWN, XHHW, or RHW2 wires. Once you get into the raceway, you're in different circumstances there. So again, any other field installed wire, PV output circuits, got conductor size ratings there and types. And then also circuits, buildings, controlled conductors. This is the rapid shutdown requirements. And so those need to be met. Again, we talked about the inverter size. Maximum inverter size is going to be 15 kilowatts, 15.36 to be precise. And that, key piece there, actually, it meets the requirements of the code. So again, smaller, there's tables in the NEC that look at the size for doing load side connections or doing supply side connections. So you need to reference those tables and make sure the size are right. So those tables you'll find in the guideline there as well. The equipment is rated for maximum DC voltage on the equipment. So it's important. Sometimes you need to look at the DC rating of each of the components on that circuit and make sure it's not extended. Typically, it's going to be 600 volts on a residential system. Sometimes you can run into equipment that's designed for AC circuits that somebody's going to try to put on a DC circuit, and that doesn't work either. It has to be rated for that DC voltage. We talked about temperature. So temperature, as the conditions get colder, actually the conductors, the circuits, the PV modules themselves produce higher output. And so you need to look at the temperature of the site to identify some of the actual ampacity ratings that are going to be needed on each of the circuits. So there's the table, you look it up based on the temperature ratings for your location. There's one tool there, solarabcs.org/permitting, that has a map. You can look location by location, find the nearest weather station. Basically, they've got data from, get those values, plug them into the tables, and you get your conversion factor. Again, the charts here outline those. This is going to give you that information that you need to verify the compliance with those charts. So obviously, if you've got a DC current, you can't exceed 600 volts in a residential system. And when you also look at the number of circuits, each series string going into the inverter, you can't exceed the inverter input ratings. So need to check that. And lastly, you need to use one of the standard electrical diagrams to accurately represent the PV system. So there's a couple of system types we've talked about. First example here we'll look at is the central or string inverter. And these are, as we said, up to 400 amp panel if it's a or 400 amp service. And if you have smaller panels, you often are going to see that size is going to be less. But the schematic here is what's going to give you that information that you need. Here's just, again, one example. These are available in the guideline as fillable format. So again, you're going to get standardized inputs to your review process for the different equipment. This looks at, giving those equipment specifications, then you put some detail in on that, and then check off some information down here at the bottom in terms of what type of wire they're using, what gauge wire, number of conductors, the conduit size, and so you can do your checks there on conduit fill and ampacity ratings and things like that with that information. Again, more detail in the notes section for each of those diagrams. This is where you cross-reference this with the detail in the manufacturer specification documents. Make sure that voltage ratings of the different equipment complies with the requirements for those areas, and you're not exceeding, like we said, the voltage rating on the DC circuits. Your disconnects are rated for that. The inverter input ratings aren't going to be exceeded, etc. Do also, obviously, again, have to provide a site plan with that. Here's the example of a sheathing attached site plan. Needs to show the anchor points, needs to show your layout. And this doesn't have to be exactly to scale, but needs to give you a good idea where those arrays are. Number of modules that are installed, shows you where some of the components are going to be, like your rapid shutdown equipment, etc. Other example plans we have, again, microinverter systems. So these are where you've got an individual microinverter or AC module on the roof. There, again, you can have no more than 4 output circuits. So those generally get combined on the roof to link together into series strings, and you have no more than 1 module per inverter. So there are some setups where you can have microinverters with like 2 modules feeding into them, but those don't fit into this box. And same 400 amp service, you're rarely going to see anything greater than that in a residential house, right? Here's again example of what that diagram looks like. So you've got all the little DC modules or AC modules, sorry, on the roof. They're converting the DC into the AC there. Go together in your junction box, combine together into an AC combiner that then goes into your main disconnect. And again, service disconnect there to be able to disconnect and work on the system. Ask for all the right specifications that you need in terms of the type of equipment. These are again specified towards that type of system. So asks information about the each of the inverters, ratings, and the disconnect ratings, etc. And here's an example site plan for a member attached system. Some of the things, obviously, again, looking at where the anchor points are, checking, some of the systems are going to need to be the anchor points spread out amongst the rafters, like this one showing. They're, alternating rafters to attach to spread that load out. And again, showing some of your main components, where your conduit's going to come down, where your entrance into the house is, number of modules, layout. You can check, again, the roof access pathways, fire access pathways, are in compliance, and other things like that here. All right, and that is the quick walkthrough of the diagram, or the streamlined process. So we've got about a half hour left. Talk real quick about Solar App, and then walk you through, quick inspection. So Solar App, Solar Automated Permit Processing, is not actually a phone app. It is a software, the web-based software tool. This has been developed over the last, really mostly the last year, but we've been working on it for well over a year before that in terms of getting the whole coalition together. Solar Foundation, through the SolSmart Award, has been an active participant in developing this. But NREL, National Renewable Energy Lab, was the lead on the software development, with the Department of Energy funding here again. And lots of input from code officials as well as the industry. Cost match. Some of the major installers in the country have been involved in all of the technical aspects of this. But essentially, what Solar App does is takes this whole process that we just showed you, and it's not exactly the same, but it was based off of this guideline as well as the California guideline and some other aspect out there. I mean, all of those, again, based off of the actual building codes and electrical code. But it is a permitting tool. It's available for free for any community that wants to use it. Certain caveats: you have to be on certain code years, which Connecticut is. And what the system does is it, again, standardizes that input. The contractor has to fill out those values, put them into the system, and it automatically checks all of those checks that you then would then normally have to do. So it verifies when they put in the inverter, they put in the conduit, they put in the number of conductors, they put in all that stuff they had to put onto those electrical specification sheets, and it then does the code calculation checks on those things, and ensures that, one, all the information that you need has been submitted, and two, that it actually meets the requirements of the array. It does that automatically. It can then instantly issue that permit. As soon as the contractor submits the information, it issues the permit because it's been verified to be code compliant. The key thing for you as well as at the community is it then prints out a customized inspection checklist with all of the components information, and then also has the attachments of it creates the site plan, or the one-line diagram to look at there. So it gives you all the information that the inspector needs to review as well, to make sure that what was submitted to the system was what was actually installed. Obviously, that is the point in the inspection, which we'll go into next. The key piece is verifying that what was said to be code compliant was what was actually put on the roof. or in the structure, right? And so it gives you that checklist. That's a real key feature of the Solar App tool, telling your inspectors exactly what they should be looking for. There are some integration with some existing software platforms in terms of some permitting process tools like OpenGov and I forget some of those, but there's some tools that we have. It can collect your fee payments for you, process those directly, and like I said, we're now just wrapping up our energy storage module on that, so we'll actually be able to do that as well. Whereas our current guidelines we just walked through don't have that yet. So leave this with everyone. We've got a page on Solar Foundation's site, but also NREL is sort of the main site, solarapp.nrel.gov. There's a number of webinars there on YouTube we've posted, and brief benefits memo you can find on our site, the Solar Foundation, talking about it and understand a little bit more about it. Not going to go into too much depth here, but key piece down here at the bottom is if you are interested in learning more about this and potentially piloting or testing out the software, getting a demo, anything like that, there's a SurveyMonkey. Fill out some basic information, asks who you are, where you're located, if you're using any government software platforms right now, et cetera, and you can get in the queue to test that system out. We're just wrapping up sort of pilot testing on it with a couple of communities. We have issued a number of permits in the real world now, and it is essentially ready to go. Working out the last couple of bugs with these testings that have been going on with the software, but it is it is ready for adoption. There are several communities that are using it right now to populate. We love to work with anybody here on the phone. Email me directly too. We can set you up, get some more info on that. All right, quick through inspection. Again, inspector's role: confirm that the system was built according to those approved plans. And if it was, then it should meet those code requirements, right? So again, same NEC articles, the building codes that are in place, but also potentially some zoning regulations that, so the standard system design, guidelines that we have didn't really talk anything about zoning. There may be some, again, areas where certain size restrictions are in place, or historic districts, or some other things like floodplains, which may require equipment to be installed at a certain height. So some of those local requirements that aren't in the model codes, your inspection, may need to look at those aspects here as well. Inspector needs to have, start off with, we think, an inspection checklist that's going to help guide them. Again, Solar App creates that specifically for the system. Otherwise, there's generic checklists that are available. There's a good one, IREC, Interstate Renewable Energy Council, has created. There's some other ones, IBTS, I used to work for, they've got a good one. I think Connecticut maybe has a checklist as well for inspections that's been created in some of their permitting guidelines there. So there's a number of good examples out there. They then take the site plan, the electrical diagram, and those spec sheets that were required for that application, and again, are reviewing those, checking that, okay, here's what the plan said. It said these were the number of modules. They were going to be installed with this type of layout, and with this type of spacing, and that the feet, the attachment points, number of attachment points, etc. Those are the things they're going to then check. They'll have the electrical diagram, so they walk through that. It's got the specifications, it's got the equipment listings there that, or not listings, but the names and the type of equipment, the size of the conductors, number of conductors, These are all things that can be verified. The number of strings, that it's got the right equipment in order here, the disconnect, the inverter, it's got a disconnect on both sides, etc. So you've got the guidelines, you need those documents. We looked at those. Go back again to what we started off a little bit with, the some of those problem areas. The main areas to focus on is the array. Now that is on the roof, which sometimes can be a challenge for inspectors. And but the other areas, the inverters and the grid connection points, those are typically pretty accessible. So we say to start with the system on, confirm that there's no faults being detected, and then have the the installer shut the equipment off, open everything up so that you can look at it, rather than having everything. If everything's dead when you get there, it needs to be energized at some point to verify it's not reading any errors, right? So we recommend starting on, and then you say, really go one way or the other, but start at the array and go down to the connection point. Sort of makes sense. Okay, sunlight's coming in here, electricity's going this way. Let's follow it all. Let's check it all in line, right? If you can't get up in the roof, certainly even like binoculars sometimes are helpful. Selfie sticks some people use. If not, other thing is another good tool that's being out is some of the tools to utilize photos of inspections, and the installer has to submit some photos of these components so that you can check those. Certainly the roof is a key piece to be able to look at, though, as much as you can. Certainly high, steep pitches, tall roofs, etc., get much more challenging. Focus on those areas where there's the greatest potential for issue. That's going to be your inverter and your connection point, and also the array. Generally, as you know, if you're an inspector, if the quality looks good, generally you're going to have better arrays. We'll walk through a few of these things real quick, some things to look at. Neat and workmanlike manner. Okay, and generally here I've got what you're looking for, or something good on the left here, and something not so good on the right. So, and this is just showing you ground-mounted arrays. Ground-mounted arrays in particular, the conductors need to be, protected from access. So the one on the left does that really well with that cage around all of those, and then the one on the right obviously does not, with wires hanging all over the place, and dogs can come up and chew on them, or kids can swing on them, or whatever. Not a good sight. Here's an example of, neat and workmanlike manner of, you can, even from the ground, you can look up under this array on the left and see there's no wires hanging down. You can see where those, you can see those standoffs. You can get a decent look under there. Hard to count the number of modules. You might need different, layout for that, different view. And then again, clearly on the left is a terrible example, but there's plenty of people out there that still do that. So that's why you go out in the field and check, right? All those components might be correct. All the conduit sizing might be correct. The wires, the conduit fill, everything, but it's just not installed properly. Thing to check, PV, modules, the numbers, is it the right type of module? Now that's a harder one, to get at, because you do need to get the module label is on the back of the module. You kind of need to be right underneath it. But does the layout, does the location, does that match the plan? The number and quantity match? And this is an area where sometimes changes do need to be made. The modules that were originally ordered aren't the ones that came in. There's, they've upgraded, they're now more powerful. Okay, well, they've got 20 of those. and each one is 10 more watts than the ones in the plans. So is the system still compliant? Potentially it still is, but it doesn't match the plans now. Something on the left there, should never have any overhang. As we talked about in the plans, everything needs to be, step back from the ridge at least a little bit. The wind underneath that is just going to rip that off at some point. Array mounting system. So you really want to check those structural connection points. Did they say they were going to stagger those array attachment points, but they didn't? They put them on the same rafter. Did they properly flash and weatherproof those attachment points? Check the cantilever here. Is there overhang? But yeah, checking those attachment points, checking that those clips that are attaching those modules to the roof were installed properly. They're actually holding them down. Can't tell you number of systems our inspectors went out on, and you can just lift the array up a little bit, lift the module up because the clips have fallen off, like you see on the right. A little bit of wiggling, wind, those things are gone. And there's dozens of those points on each system. So again, roof penetration, slashed and sealed properly using the right equipment for the job. Ones on the left are good, ones on the right are not. You can't just screw directly into a deck. You got to seal that, weatherproof it. And even if you use a weatherproofing device like that flashing up there, it needs to be installed properly. That is for composite shingles. It's supposed to be overlaid, underneath with shingles going over top of it. You can't just put it on a flat roof and think it's going to work. Array exposed. This is a big one, and it's a harder one. Again, if you're not on the roof to be able to see, but exposed cables need to be properly secured and supported to prevent physical damage, and to prevent, as we see here, debris building up, catching in there. That's a great little rat's nest. A little mouse or squirrel dig their little hole in there, start chewing on those wires, and you have a combustion event very quickly. You have loose hanging wires. They're going to abrade, rub over time against your concrete or not concrete, composites, or against the edges of things. Everything needs to be secured and tied up, neat and tidy there. Wire management is one of the more challenging things for installers to do. Conduit, conduit needs to be used in once you get outside under the array. Need to go into conduit, that DC circuit there in most cases. Again, needs to be installed properly. Plenty of examples out there where people just run the wires over the side of the roof and then enter a conduit somewhere maybe, and but that's just not good. Proper type of conduit as well. Another big thing with conduit especially is the length of conduit and making sure you've got expansion joints and things like that. Again, conduit, neat installation, and actually on the roof needs to be raised above the roof surface, which you do see on the left as well. There's rules around that, and that should be specified there. Fire access pathways, again, according to the approved plans, there's a variety of ways to do this. But there's setbacks from certain roof edges that generally are going to need to be followed. There's setbacks from the roof ridge to allow the firefighters to vent, and then pathways from the one side of the roof at least need to be up there. So yeah, details in our guidelines, different options for how to comply. Inspector's job is to make sure the approved plans again were followed. Fire classification, again, a thing that's checked in the guidelines in the application form. you don't check this by putting a burning piece of, they call it the burning brand on top of the module. You check this by just looking at the specification sheet and making sure it's listed. The modules need to match the fire classification of the roof to be in compliance there. The text on the left is how they actually get the classification. Grounding and bonding, big area, lots of different components in terms of, what you're looking at here. Different ways that the material can be grounded and bonded. Again, in the guidelines, making sure that that system was listed as a UL 2703, and then now in the field, you're verifying that it was installed properly. Some things to look out for, obviously, are incompatible materials, which you see on the top right there. You see some rusting already starting to happen, among some other issues with that installation. And then hard to tell on the right if you're not familiar with it, but the bottom one is there's a grounding clip that when you attach that clip, the mid clamp there to ground, or it's a structural attachment, but in doing so, it has a little metal thing that pierces into those modules and actually electrically bonds them to that. So you have a whole connected system, but that particular clip there did not quite make it where it was supposed to be, and is sort of bent and deformed down there at the bottom, which is now not electric. It may be structurally sound, but it is not electrically connected. So just a couple examples of things you're looking for there, and a relatively common one you see. Again, equipment needs to be listed for PV systems, and the inverter there needs to be listed as utility interactive to be able to comply with that. So again, you'll see those UL listings on the different equipment pieces. Conductors, cables, conduits, etc., need to be sized correctly, need to have the right insulator type, need to have the right number in the conduit. All of those need to match the plan. So again, outside, you're good with that PV wire in an exposed situation, but your other cables that would be used once you get in the junction box, you can't do that when it's out in the roof exposed. And also supply, SJO or cord is not approved for the PV wire or those applications. Overcurrent protection is critical, important, obviously, and general and PV systems have what's called the 120% rule, if you're not familiar with that. So that's the sum of all of the circuits in the panel cannot exceed 120% of the total array or total bus bar rating. And so that limits the size of the circuit that you can put a PV array on. This is where you get to that maximum 15 kilowatts that can be put on the 400 amp. And also actually that's the next slide, I think. So, again, the overcurrent protection devices match the plans that should have been checked for this. Here's the, this again, overcurrent protection. Minor one here, but again, you run into pretty regularly. The fuse on this one is not rated for 600 volts of DC. Maybe you're rated for 600 volts. It says that really big on the side of it, but that is its AC rating. Does need to be rated 600 volts of DC if it is used in a DC circuit. Again, any overcurrent device there has to match that. Disconnects are installed according to the plan as well. So you need to have disconnect on either side of the equipment in order, so typically, your AC on one side, DC on the other side for an inverter. and need to be, accessible, viewable from that location. Example on the left, the right, left, you can see that clearly, one on one side, one on the other. The one on the right, one of the disconnects is actually outside, and so not right there next to the inverter where it needs to be. The inverter input, if you're doing a load side connection, the free circuit breaker that you're putting in has to be on the far end from where the bus, from the main breaker is. So you can't put the inverters, can't put the PV array into any of the other slots. It has to be on the bottom slot. Labeling, lots of labels required all across the board for each of the components. Sometimes the conduit as well needs to be labeled, and certain requirements on each of those. Labels also have to be, durable for the environment in which they're installed. They have to be permanent in certain areas. So it's, the types of material that's used, et cetera. Some do require permanent plaques versus you can't just write with a Sharpie marker on a sticker. So, there are a number of different label requirements. There's also some good guides here. Again, IBTS has one. Hellerman-Titan's a manufacturer. They actually produce the labels, but it's a great guide for, again, what's needed in those systems. Labeling is the biggest one where there are deficiencies in systems after they've been installed. It's one that, there's some good checklists for, again, to check. The system does need to be grounded to the grounding electrode, as in the approved plan. There are a couple different ways to ground things sometimes, depending on the code you're following, the type of system. Generally, it's okay to attach to the existing ground. Sometimes you may need to do additional ground for the system if the existing ground is not secure and in good shape. So, that is an important piece to look at in that process. And we got one or two more here, two more, I think. Access. So access space, working space. Where things are located, are you able to, have the proper working space around them? There's different, there's requirements there for different components. And, again, some of the spacing is also needed for how far away things can be. For instance, like the disconnect, the switch, where that can be, within like the 10-foot rule. There's others. The automatic disconnect needs to be, within a certain distance on the roof. So distances needed. Yeah, the rapid shutdown, that was needs to be, be able to shut down the array within a certain distance of the array. So it needs to be installed there sometimes. And I think that is it. Here's a quick summary of some of the resources I mentioned. Again, we'll give you this copy of this presentation so you have it. Good places to find some of these checklists, the labeling guides, some good books to learn some more about stuff. Obviously, our SolSmart website has lots of resources on there, templates for all of this as well, and tons of good information out there. Particularly IAEI magazines. Specified John Wiles, he's done a lot. I'm sure there's other authors on that too. Oh, I need to add SEAC now to this. Sustainable Energy Action Committee is putting out some, starting to put some best practices and stuff out as well. And that is it. And I am right on time, it looks like. So here's my contact information again, Richard Lawrence. We've got, like I said, other staff Bill Brooks and others that can help with some of the more technical questions. We've got people can help more with some of the guideline implementation, some zoning, planning reviews, all that type of stuff too. So feel free to reach out to us. Thank you for your time, and happy to stay on for a few more minutes if anybody has any questions. Otherwise, thank you again.
Hi, Richard. It's Pam Roach. That was fabulous. Thank you so very, very much. If anyone has any questions, please speak up now. Otherwise, stay safe and stay well. Is everyone unmuted?
Looks like everyone is muted, but I think
Okay.
we could at least stop recording, or well, yeah,
That'd be good.
fine.
I didn't know if maybe if anyone has any questions, I think they could just unmute or type it in, right?
Yep, or you got my email right there, rlawrence@solarfound.org.
There you go. And you know how to get me, everyone, pdwickyroach@gmail.com. But I think everyone has that. So great, Richard. Have a wonderful day. Thanks so much.
All right, great. Thank you.